Hello, my name is MD Burhanuddin. I am a recent graduate in Material Science and Engineering from the University of Rajshahi, Bangladesh. I am looking for Masters or PhD opportunities or Masters PhD combined opportunities in semiconductor, energy and optoelectronics and integrated circuit, CMOS, etc. In this type of fields I am looking for opportunity. Today I will show you how to analyze XRD data which is obtained from laboratory. So let's start it. Here we have the structure, as you can see. Sorry, this is not structure, this is laboratory data. So this is laboratory data and the data is initial value is 10, increment is 0.01 and the final value. So and the whole data. So I cannot plot it in Origin Pro or any other software. So I have to modify the data in X column and Y column. In this presentation I will show how to mesh or find the phase and other things, and in the next presentation I will show you how to perform Rietvelt refinement using foolproof software. Okay, so I have to modify this data. As you can see, the data is in text format, so we have to change the format to DAT because the foolproof wind plotter only support DAT format, so we have to change it. So let's we can delete it, like we don't need this value, or keep it as it is, we don't have a problem. So save as dot and save as type all files. Okay, our data is now in DAT format, so we have to open wind plotter software. So I will start from the beginning. Okay, now I am going to open foolproof suite. Okay, then I will open wind plotter, then file, open pattern file, and this is the file is not XY data. We have initial, step and final, T initial, T step and T final. So select this one and click OK. We have the web of talent, and now select this one and open. This is our pattern file. Okay, now we have to save data as XY file or XYY file. So I will save it like this one. Okay, right header, we don't need it. Okay, now go to the file. Possibly this is the file that we created just now. Okay, as you can see, our data is ready. So our data is ready, but I will mesh this data with standard JCPDS card which is by Expert High Score software, but Expert High Score software only support ASC file. So I will modify this format, save as, select all file, and then just .asc and then save. Okay, our ASC file is created here. Now I am going to open Expert High Score software. Okay, our Expert High Score software is opened. Now I just drag and drop it in the Expert High Score software. Okay, I have to select the peak initially. I can do it automatically by putting some initial value or manually. So automatically is preferred. If automatically cannot detect the peak, then I will select manually. So let's start search peak. since I have used this software, so initially there is some value. We can tune this value minimum significance 7. It depends on the total counts number. If the counts number is very low, we have to select the value from 1, 2, 3, 4, and we can tune it. And if the value is more than 10,000, we have to select 20, 10, or this type of things. Our main idea is to detect the peak. Okay, if we search peak, then we can see there this peak is detected, this peak, this one. Almost all peaks are captured, so we don't have any problem, just accept it. Okay, now we will search and match it. Search and match execution. So this is search and match. We have to restrict the file because our file is had some doping elements. What is our file name? We have lithium, nickel, manganese, titanium, cobalt, and oxygen. So basically we have lithium, nickel, and manganese, manganese, titanium, cobalt are occupied the same lattice site of nickel. So the base material is nickel, so we don't have to worry about this. So we can just put lithium, nickel, and oxygen. These are enough. Okay, lithium, nickel, oxygen. Okay, but if we want to sure that cobalt, manganese, and other things are present, we can also select that. But if our score, I will show you, score is satisfied, so we will not worry about that. Okay, load, then search it. As you can see, only 65% score is matched here. This means this standard data has the same structure and the same occupancy and the XRD pattern like our the match score is 65. So we can expect that this data and our data matched as 65%. So we will not accept this value. So we will just again modify the restriction. Clear. One more thing, we cannot select the data or select the element from the periodic table. Just we will keep all the materials are clear, and then we will search it. In this case, our program will search accordingly, search the peak according to our pattern in 7 lakhs data. So 7 lakhs data, to search this will take a lot of time, but we will do this. Okay, let's search it. So as you can see, the searching result is almost 0%, only 0%. It will try to 100, so it may take some seconds. So please stay tuned. Okay, 25% is done and 75% yet to be done. Okay, our matching is done. So this is lithium, gallium, oxygen 2. So our material is matched with lithium, gallium, oxygen, so we will use this one and click OK here. Okay, this is our structure, so just save it. And lithium, gallium, oxygen. Okay, close. This is our JCPDS card, standard card. So as you can see, this has the highest matching, 77%. What happened? Okay, 77%. So lithium is lithium and gallium, as you can see gallium. So all these materials, nickel, manganese and titanium and cobalt, are occupy the same site of gallium here. So I will simply plot this data in Origin Pro software. Okay, let's start. Okay, this is our data. Sorry, our data is ASC format. This is our data. Control All, Control C, and just Control V. One more thing I want to say, we just compare this with JCPDS card, but in our data the y-axis value is higher, so we don't which is arbitrary unit, so the unit of this column has no significance, just we need this value. So I will normalize this data. Normalization can have a lot of options, but I will select 0 to 100 because as you can see in the JCPDS card the highest value is 100. The highest value intensity is 100. So if I put the normal data obtained from laboratory, it will misinterpret because 100 intensity is nothing compared to 4000. So I have to keep it mind. So I will modify this, normalize the y-axis value. Okay, so we don't need it, delete it. Okay, now add extra column and I will put this JCPDS cards data. Just copy, then Control V. So here we have 2 theta from the JCPDS card and the intensity, and we have our data and normalize. So I will plot this one. Sorry, this I have to select this as X. So this one, sorry, this one, this one. Okay, now plot it. Our plot is done. So I have to modify. So 10 to 70 is okay, but I have to modify this data group. Select layer, stack, individual. Okay, now I can move it data. So since our each column value highest value has 100, so I will select this as 200 and I will keep 50 more because I have to write the peak's name. Okay, okay, fine. Independent, then drop lines, vertical, apply. Okay, and line, straight, no line. Okay, we have the pattern now. And format page should be 100 because in journals in journals we have to select the image for A4 page. So in A4 page the 100 millimeter is well suited because if these value are 10 and 11 points, so we have to select 100. Then view, show, frame. Okay, fine. Now I think 10 to 70 is okay because our main peaks are between this value, and we don't need it because this is arbitrary unit, intensity dot arbitrary unit. Okay, we have to remove lines out, no line, no line. Okay, fine. I have to select this one as 1. I want to change the color. Okay, fine. I want to okay, from here drop lines and to select 1 and this value should be magenta. Okay, fine. and our card name is Control C and put it here, and we don't need it because these are from. Okay, we have to write the subscript and superscript accordingly. Okay, our file is ready. This is 2 theta. 2 theta unit is degree. Okay, this should be as 10, this should be as 11. Sorry, this is 10, 11, and this should be 10, and should be Times New Roman. Times New Roman, Times New Roman, and it should be 10. Okay, fine, this should be also Times New Roman. Okay, now we have to write the peak name. As you can see, this peak is X is 18.38. 18.38, so the peak name is 003. I have to write it 003. 003. This is 10. This is okay. Wait a bit. Okay. This is 0010. I'll write the main peak here. 36.13. 36.13. So the peak is 101. Control C. (101), and the little bit peak is 37.75. 37.75. So 10 minus 2. I mean 102 bar. Okay. We have to add bar, so 102 bar, 102 bar, add bar. Okay, okay, fine. Then another peak is 43.73. 43.73. So the peak is 104. Control C, Control V. 104. Okay, this one 47.81. 47.81. This is 105 bar. Control C, Control V. 105 bar. Sorry, 5 bar. Okay, fine. Now 57.62. 57.62. This is 107. 107. Okay, we have two peaks here. Under the peaks, 63.29 and 63.90, 108 bar and 110. Control C, Control V. C, Control V. Let's check it again. 108 bar. Okay, fine. 08 bar, and this is 110. Okay, fine. And the last peak is at 67.12. 67.12, the peak is 113. Okay, Control C, Control V, 113. And we have to write the reference code here. So what is the reference code? The reference code is this. Just copy and paste here, and we have to write it 10. We have shortage of space, so this is the this is the reference code. We can also write the space group here. So what is the space group? The space group is R3/M. Copy. Maybe we can write like SG is dot G dot space group. Okay, so this is our XRD card. We can see this, and in next presentation I will perform the Rietvelt refinement and show you the grain size, micro strain, dislocation density, and the actual crystal structure. I mean the lattice parameters of the of our structure, not the reference code. This is the reference code or reference structure. As you can see, this is their lattice parameter. So since I have shortage of time, I will keep it. I want to end the presentation here. In next presentation, I will perform Rietvelt refinement, where I will show the rest. Thank you.